Okay, so I'd like to begin by thanking the organizers for organizing this wonderful meeting and for having me here. So I'll be talking about the energetics of quantum Brownian oscillators. So most of this work that I'll talk about has been done with Malay Bandyopadhyay at IIT Bhubaneswar and Jasleen, who is Malay's PhD student. And so we'll be talking mostly about the strong coupling limit, but towards the end, I'll mention about the weak coupling limits, which appears in this preprint, which we put earlier this week. So this work I did jointly with Shushanta Dattagupta. So recall that the classical Brownian motion problem is as a prototype of a microscopic system plus bath scenario. You have a suspended particle, which is your system of interest, and you have a heat bath, which is your surrounding fluid. The problem can be generalized to the quantum scenario where you have a quantum particle, which is your system of interest, and you have a quantum heat bath. So the most, the generic Hamiltonian looks like this, where HS is the system Hamiltonian, HB is the Hamiltonian describing the bath, and these are the interactions. So there are mainly two ways to approach this problem. One is the Heisenberg picture formalism, where you talk about equations of motions for the observables characterizing the system by tracing over those of the bath and substituting them into the system. And the other is the Schrodinger picture formalism, which talks about, say, a master equation for the reduced density operator. So we'll talk about the Heisenberg formalism. So the model is a harmonic oscillator, which is the system, together with the bath and the interactions. So here we see the interaction term. If you open the square, we get a QJX summed over all J. That's my bilinear coupling. And you also get a x square term, which is to compensate for bath-induced frequency shifts and all that. So this goes under many names, the Feynman-Vernon model, Caldera-Leggett model, Ford-Kaczmarzyk model, also sometimes the Swansig model. So if you find out the Heisenberg equations for the system and the bath operators, integrate the variables of the bath, substitute them back into the system, you get something like this. This is called the quantum Langevin equation. Mu t characterizes memory-dependent drag force, and Ft that we had in the right-hand side is a bath-induced noise. And note that you have an x0 dependence in the definition of the noise, and you average this noise over an initial distribution, which looks like this, where you have a system bath coupling at the initial instant. So essentially the system and the bath are not decoupled at the initial instant. So we don't have things like Born approximation here. So it's like a strong coupling situation. And when you perform these averages, you get these correlations and commutators. So the mean energies are computed from the equal time correlations at large times. So for instance, the potential energy comes from the position autocorrelation, and at equal time, take the time to be big. And similarly, the kinetic energy, these are the expressions. These are rather well-known expressions. And alpha is called the susceptibility, and the curly E that you see is the mean kinetic or potential energy of, say, a heat bath oscillator with frequency omega. So essentially, in a sense, the heat bath is giving you a frequency broadening, as in if these were delta functions, the energies would just be the usual energies that you get in the statistical physics of an oscillator in the canonical ensemble. So a consequence of coupling to a heat bath is a virial theorem of this kind, where you get the kinetic energy is not equal to the potential energy, but you get terms like this. This term here is the long time equal time correlation of the position operator and the random force, which does not vanish for a non-Markovian scenario. So this is essentially work done, and this is the work done due to the damping force. It turns out that if you take the classical limit, it doesn't matter whether you are taking a weak coupling limit or a strong coupling limit, you get the same result for the kinetic and the potential energies, which are kBT over 2. It turns out that the energy that we get as the sum of the kinetic and the potential energies is not the thermodynamic energy. The thermodynamic energy comes from this definition, where you start with the full Hamiltonian, the system in the bath, and this is described by a full density matrix, not traced over the bath. So if you average this with respect to the density matrix of the bath, of the full interacting situation, you get a certain average. You subtract the energy of the bath from there, what you get, you call it the internal energy. And in general, the U that you get here differs from the E, especially when you have non-Markovian damping, as in the case of the Drude model. However, in case of ohmic dissipation, where the friction kernel is a delta function, they become equal, but they diverge because the kinetic energy blows up. So here we have plots. The violet one is the E, and the yellow one, the black dashed one rather, the black dashed one is the U, and the yellow one is the energy that you get from the partition function that you get it from the by evaluating the so-called influence functional and using Euclidean path integrals. It turns out that the U that was defined here, that agrees with the thermodynamic energy, not the violet one. So these are plotted with respect to the damping constant, and they increase monotonically with the damping constant. And here we plot them with respect to alpha, which is the ratio of h bar omega naught over kBt. So when you take alpha goes to 0, which is to say you're in the classical limit, these all merge to 1. So 1 is just the result kBt. So all the energy functions become kBt. Otherwise, these are increasing. So the classical case, whatever energies you have when you go into quantum mechanics with finite dissipation, the energies are more. So finally, let me conclude by talking about the weak coupling limit. So the weak coupling limit microscopically talks about setting the coupling constants to be very small with respect to this mj omega j square, in which you can approximately factorize the initial density matrix in a system and a bath kind of factorization, which you get in the Born approximation. In terms of quotient parameters like gamma, it corresponds to setting gamma goes to 0. And this, if you substitute all these, this gamma goes to 0 back into the expression where we had the susceptibility and those integrals, you get a delta function. So essentially, we get that the kinetic and the potential energies are equal to each other, which is familiar from statistical mechanics of a quantum oscillator in the canonical ensemble. I should mention Markovian approximation for the noise. You can make a Markovian approximation for the noise in a weak coupling limit, which is to say that you're talking about the system and the bath weakly coupled, such that only those bath excitations which resonate with the frequency of the system are relevant, wherein you can pull out the Cot hyperbolic outside the integral, you get a delta correlation. And if you compute correlation functions with this, you get the same results at long times. And this weak coupling scenario matches exactly with that of Girish Agarwal. He obtained it using a Born Markov master equation. So to summarize, I mean, strong coupling with the bath gives you many interesting results. And in particular, you get inequivalent perceptions of the energy, although you can get weak coupling results by taking appropriate limits after having computed different quantities. Yeah, so, and yeah, at weak coupling, both E and U, they reduce to the familiar expression. Okay, so maybe I'll take questions.
Since there are no questions, let us thank the speaker.